So the first step to running any crystal grower simulation will be to partition your structure into units of growth. There's two options for units of growth in Crystal Grower. You can either use a tile-based system, which is based around natural tiling, or you can partition your structure using the simplified net, which we call net structures. But where did this partitioning system come from, and how do you know the situations that you're supposed to use net crystals in and the situations you're supposed to use tile crystals in? So I've got a few slides here explaining the origins of each approach, and a summary of when you should be using each approach. And both of these approaches rely on using the software Topos Pro, although you can also use Crystal Maker for the net approach. There are several videos explaining how to partition your nets using Topos Pro. So once you've decided on a scheme that you should be using, watch those videos to understand how to actually perform the partitioning. So I'm going to start with the tile partitioning, because that's where we actually started when we were developing Crystal Grower, as we were trying to design a general scheme for growing lots of zeolites. The two papers that are essential reading for understanding natural tiling are shown on the screen here. One which explains natural tiling in terms of nets in general, and one which explains natural tiling specifically for zeolites. So taken from that zeolite paper, there's a nice hierarchical diagram explaining all the different types of building units that have been proposed for zeolites. So I'll quickly run through these and then explain why we're not using any of those. So composite building units pretty much encompass everything, so they're too general. Anything can be a composite building unit, and they encompass all the other building schemes. Secondary building units is probably one of the most famous ones. They're not general enough. You can't partition a structure generally just using secondary building units. Some of the most famous ones you can see on the screen there. You've got the double 4 ring, which is like a cube, and you've got the double 6 ring, which is a hexagonal prism. So there are a few lesser known ones. So this one, the CCBUs, the constituting composite building units. There are some arbitrary choices involved with combining nodes and edges, and they can be infinite and finite. They don't lend well, again, to being a general building tool. We need something that has strict rules and can be algorithmized. So anything arbitrary immediately eliminates the use of this building scheme. Then we've got periodic building units. They are a subset of CBUs, which involve some periodicity, but these again can be infinite and finite. Again, not suitable for a general building scheme. We've got fundamental building units. These actually do have some kinds of rules, but they only apply to fundamental chains, and they're infinite or finite, so we can't use those either. Polyhedral building units are probably the second most famous unit. A lot of the cages shown here are quite famous polyhedral building units. You've got the sodalite cage at the top, or the beta cage, an alpha cage, which you see in zeolite A, and you've got your nice faugesite cage, which you see in zeolite Y, zeolite X, and faugesite. But there's no general method for breaking down structures into these units. So which scheme is the best out of those? The answer is none of them, because they all have some arbitrary decisions made in the process when you break down a structure into them. So that eliminates all possibility of using them as a general building unit, because you can't algorithmize them. So let's move to what we see in reality. So in 2010, our group did some AFM studies in situ on zeolite L, which is a type of zeolite framework, and they scanned back and forth across one line continuously where there wasn't any dissolution taking place, but the tip of the AFM cantilever caused some local dissolution to happen. And they found that these levels of dissolution, as you cut through the terrace slowly, all corresponded to terminations with what we call closed cages. So those closed cages are all units where each corner, or tetrahedral atom, because this is a zeolite framework, is connected to 3 other tetrahedral units. So that's called Q3, and that's what defines a closed cage. So a cube, for example, is a Q3 cage, because all corners on a cube are connected to 3 other corners. So that suggested that closed cages are rate-determining steps during crystal dissolution, and that they are metastable. So they should be rate-determining steps during the crystal growth as well. So they make a good candidate for a general building scheme for these types of crystals. The same thing was also observed with transmission electron microscopy. You could see the terminations at the surface were also primarily Q3. There's an issue where less than 1/4 of all known zeolite frameworks can be built using closed cages only. So we need to come up with a better scheme which encompasses closed cages and also what we call open cages. These would be cages that have some Q2 units in them, but still the lowest energy structures that can be used to construct the whole framework and any framework of the known zeolites. But luckily a scheme already existed known as natural tiling. So there's some examples of some natural tiles there. And natural tiling is a building scheme which follows some set mathematical rules. So there's 4 main rules here. The symmetry of the tiling must coincide with the symmetry of the 3D net. Faces must be strong rings, so all tile faces are not sums of smaller rings. All strong rings that aren't faces intersect each other. And the final rule, if multiple tilings satisfy the first 3 conditions, then they combine the tiles together until they combine to form a larger unique tiling. So you start putting tiles together until you get a unique natural tiling. So that's where the word natural comes from, because it's unique. You can't have multiple natural tilings for a structure, but you can have multiple equivalent tilings. So here are some diagrams explaining rules 2 and 3 respectively. There are a lot of rules about how you define rings. The only one that is a strong ring here is C. Then this is a spanning tree graph of a cube where you reach every vertex without going across every edge. This one, C, is the only thing that's a strong ring because you can see it's a ring and it's not composed of other smaller rings. This here is called a cycle because it's a sum of 2 rings. So E is a ring because it's composed of more than 2 rings. 2 rings makes it a cycle, like D, but there are 3 here. But it's a combination of more than 1 ring, so that makes it a weak ring compared to C, which is a strong ring. And F is also a cycle, same as D, if you include these 2 here as a ring, and this one here is a 4 ring. So that's a cycle again, because it's 2 rings, really. This reference below explains in a lot more detail about rings. And then this one on the right here shows you rule 3 in action. So this is a tiling for a structure. So if you look at one of the tiles that makes up the structure, you can see coloured here that we have strong rings. These are 4 rings, even though they're shaped quite strangely, they are strong rings because they're made up of 1 ring. And then you can see this satisfies the rule of all strong rings that aren't faces intersect each other. So you've got 2 other 4 rings here, but they intersect each other. There's also a case where you add an extra rule, which is rule E, and this is that you can override rule B in some certain situations. And there's 2 zeolite structures which are examples of this here. This doesn't come up that often, but it's something to be aware of. There is also a video showing examples of when you use this in the Topos video series. So now let's move on to nets, which are a little bit simpler to understand than the natural tiling. So instead of partitioning the crystal into larger units of growth, we partition the crystal into the actual growth units. For example, in an ionic crystal, you'd split it into the composing ions in the crystal, or in a molecular crystal, you'd split it into the molecules that compose the crystal. So we're simplifying these down from lots of atoms to simple nodes. Then we need to find all the interactions between these nodes. And these interactions become our edges. So what we're doing is we're taking a net, which is our crystal net, and we're simplifying it. So we're creating a simplified net. Hence the approach being called net. When you partition structures in Topos, you use the Voronoi-Dirichlet polyhedra approach. And this paper here explains in a lot of detail what these polyhedra are. It's a review article, so it's quite long, but it teaches you a lot about these polyhedra. So what exactly is a VDP? So it's better to start explaining it in 2 dimensions. A simple version of a VDP is shown on the left here. So if we start from our central point here, and we have a set of points surrounding it, which are marked by X's, we can define boundaries where everything within the boundary is closer to the original point than any of the surrounding points, up to a certain distance. So you can see these X's are too far away. So there are no locations here which show that it's closer to the surrounding point than the central point. If you have a set of surrounding points, you can define a polygon in 2 dimensions. So if we move to something that looks a little bit more like a molecule, you can see that it gets a bit more complicated to define, because your molecules aren't just points, there's a few points, you have bonds too. But the same concept applies. Everything that's within this polygon is closer to this molecule than the surrounding molecules. There's a nice interactive diagram here where you can actually make a Voronoi in real time, which I'll show you now. So here I have a blank square. If I add some points in, so that's our first point, there are no surrounding points, so everything's going to be closer to this point than any surrounding point. If we add in a second one down here, you can see we've got a nice partitioning line running straight through the square. And then you can add a few extra points. You can see you can get something rather complicated. So if you imagine we expand this into 3 dimensions, we're now able to look at crystal structures. So there's two methods that you can use for treating net crystals. You can either look at simple distance ranges running from centers of molecules or ions to each other, which can be done using the crystal maker approach too. And this is perfectly fine when you're looking at symmetrical molecules, because the centers are going to be roughly in the right place. And if your molecules are symmetric, then the interactions on both sides are going to be equal. But this approach does miss out on any local coordination. But the Voronoi polyhedra approach, which I've just covered, will account for that. So this is very important for asymmetric molecules. So if you only used the center-to-center approach in an asymmetric molecule, you might miss out on some interactions that are actually closer than you'd expect if you were measuring just the centers. So in Topos Pro, this is represented by two modes. You can use the solid angles approach or the domains approach. I'll discuss this in detail in another video. But these boil down to the size of the VDP face relative to the other faces in the VDP. And the larger the face is, generally the larger the interaction is, because the species are generally closer together. Or you can use distance ranges, which can be used in Crystal Maker, but are also supported in Topos Pro. The differences between these are discussed in another video. There are some shortcuts in Topos where you can generate lots of structures, where you consider different strengths of interactions by cutting off different size Voronoi faces. So you can get a good quick description of lots of different coordinations. But this is again covered in another video. And if you want, you can create your own adjacency matrix in Topos Pro, where you define all of your connections manually between certain atom types, similar to your distance ranges that you use in Crystal Maker. But which approach should you use for which structures? So the main example I presented in this presentation were zeolite structures. So that can be extended to cage structures that are similar to zeolites, so zeotypes like sapos and alpos, and titanosilocates, known as framework materials. They should all be treated with natural tiles, but the key point to look for is the importance of which atom lies at each vertex. So if replacing some connections at each corner of a tile or cage roughly contributes the same energy to the overall structure, then you should treat them with natural tiles, because it's a good simplification of the system. There are additional features where you can change the energy weighting for each atom type at a tile vertex or cage vertex, but generally you only want to use these with framework materials. So when do you want to use the net approach? The answer is pretty much everything else. So any situation where atoms are not interchangeable, or ions are not interchangeable. So for example, you can't just replace a sodium with a chloride in a sodium chloride crystal structure, so their energies are different, and they're only replaced at defects in your crystal structure. And another extreme example, a metal organic framework structure, which technically is classed as a framework material. You can't replace a linker unit in the crystal structure with a metal unit because it disrupts the crystal structure completely. So most situations you'll be using the net approach, which can use the VDP approach, or the geometric or distance-based approach. 9 times out of 10 you'll be using this approach. Natural tiles are solely reserved for really complicated unit cells, which can be built by cages, where you want to study each unit at a time, rather than breaking it down all the way to the atomic level, as you would for net-based structures. So I hope this video has given you a good idea of where these schemes came from, the theory involved in them, and the situations to use them in. There's a series of detailed videos for both tiles and net-based structures explaining how to partition them, and any complexities that may come up while you're doing this. So I'd recommend you go and watch those videos. But to summarize again, the majority of structures will be tackled using the net partitioning approach, and there's only a few situations where you'd use the natural tiling approach, specific to the materials listed here.